Good morning and welcome to a new series of lectures. This time we are talking about model-based fault diagnosis. So to put things in context, let us look again at these slides that we used several times. So today in this lecture we are introducing how to extract features and generate symptoms. And in model-based fault diagnosis, the symptoms we are generating are called residuals. In the next one, we are showing how to take these residuals and evaluate them using suitable thresholds for reaching fault detection. So if we compare what we are going to do today with what we have done in the last lectures, so we can see some parallel and some differences. So the parallel is that, of course, in both cases, we are taking observations from the system that we call plant here. But in the case of signal-based approaches, we are just assumed that we can extract some features such as the actual empirical mean and variance. So let us add here the hat here. Okay, so we can extract these empirical mean and variance, and we can compare them using a suitable test to nominal values, that is the nominal mean mu0 and the nominal variance sigma 0. This is what we have done in some of the probabilistic tests that we introduced. But apart knowing nominal values of them, we have no model of how the plant is behaving. We have just a description of its output in some statistical terms. Today, instead, we are introducing more advanced methods where both the residual generation, that is symptoms, feature extraction and symptom generation, and the threshold generation that is used for the test here, well, both these steps are based on a model. So the idea is that we take observation from the plant, and using a model, we compute the residual, which is the difference between the actual behavior of the plant and what the model is saying should be the nominal behavior of the plant. So this R is a difference. Let's say actual minus nominal, but this nominal is computed using the model. And the same model is used to generate, online or offline, the threshold, which is an upper bound on the maximum value of R that we expect in normal conditions. So the threshold that we denote R over bar represent the physiological limits. So everything above these is going to be pathological. And so when this happens, we issue an alarm. In case we have a residual that is not a scalar, but is a vector, of course, we can use one of the approaches that we have seen previously in the lecture on limit checking for introducing an evaluation function and turning the problem of evaluating a vector into evaluating some suitable scalar. So indeed, the tests that we implement here, as well the tests that we implemented here, they were based on limit checking. So what is making these smart is how we generate the symptoms and how we generate the nominal values or the upper thresholds in this case. So the logic is simple, but this step is complex. And today, this step is going to be even more complex than previously, but we are going to see how this is going to provide some good detection properties. But now let us move forward and let us introduce in some more formal way the main characters. And we start with the residual. To do so, we need to rewind and go back to something we presented in one of the first lectures, the structure of the system. So you remember that we introduced a bipartite graph to express the structure of a system, or to be more accurate, the structure of a model representing the system. So in this structure, we have a set of constraints, that is equations of our model, and sets of variables. Variables can be both known if we measure them or we know them. So in the case of the input applied to a system, this is known because the control system knows what input is being sent. Or you can have measurements of a variable. So to make this example here more relevant, let us assume that we have a simple system with one input and just one state variable that is also measured. So here Z2 is representing the state variable, which is actually unknown. We have no access to the actual state, but we have access to measurements. And C4 then is the equation implementing the measurement. And C4 can be as simple as saying that Z3 is equal to Z2 plus some noise, and let us call this noise eta. So eta is some random variable representing noise. So we have the input to the system, some equation telling us how the state is evolving, and then here we measure the state. So Z3 is known, so Z3 is known, and Z1 is known. Okay, why are we interested anyway in the structure of the system? Because as we said previously, the structure of the system is interesting when we are looking for one thing called analytical redundancy relations. Analytical redundancy relations are different paths along this graph that allows to compute the same variable in two different ways. So for instance, here in this example, you see how I can compute Z2 either going through this path or this path. So if I have two different ways of computing something, I can compare them. If everything is behaving nominally, I expect that these two different ways of computing the same variable will provide the same result. Of course, this is assuming that our model is consistent and correct. But this is the first assumption. So if our model is consistent and correct, and if I have two ways of computing the same variable, I should get the same result. If it is not the case, something is broken. But actually, not all the different analytical redundancy relations that we can find are useful. So the ones that are useful are the ones where I compute the same thing in two different ways using two different sets of known variables. And this is the key thing, because I need known variables to actually compute this. So I cannot compute them on variables that I don't know. But in this example, if I consider this blue path, I can compute it using Z1, the input to the system that we assume that we know. This other path, the green one, I can compute using Z3, that is a measurement of the output of the system. And both, they are ending here in Z2. What we assume is the internal state of the system that we cannot directly measure, but we can compute it. So we can compute it once. This would be the direct path, so I'm evaluating the model forward. Or I can compute it like this by inverting the measurement equation, which in our case is very simple. So both ways should give us the same value for the internal state. There is actually a caveat. So if you look at this measurement equation, there is still one unknown, that is eta, the measurement noise. But let us assume for now that eta is conveniently small, such that we can ignore it. So if we can ignore it, then these two different paths should provide the same result. If it is not the case, it means that something is broken either in this equation, or possibly this one, or this other equation. And this means that there is a fault in our system. The difference in these two paths, in this example that we have, is that if you go the blue one, you are making a prediction. So you start from something that you know, the input to the system, to predict something that is happening to your system. In this case, you're using actual information that you have that is already updated to go back and check the prediction. So if the two things are not matching, it means that something in the way that the system evolved is not correct any longer. So it is not longer matching the model. So if we are in this situation, and we can do this check, then we can formally introduce the residual, because the residual R is the difference between the output of two analytical redundancy relations producing the same variable and depending on different sets of known variables. So indeed, in this case, I can take the difference between the Z2 predicted over the blue path and the Z2 reconstructed over the green path. This difference is the residual. And this is the thing that should be 0. It is not going to be exactly 0 for several reasons. And one of the reasons is the measurement noise. So there are different ways of finding analytical redundancy relations. And we're introducing a few using this simple example. One way, now we have different paths shown here, but still let us assume that Z3 is some measurement of the output of the system. So we have one way that is direct. So we start from the inputs of the system, we propagate forward the model, we get to a measurement, so this is the blue path, and then I compare that with the measurement that I have. So now the green path that is shown is just shorter than the previous one, but we mean exactly the same thing. So we have a measurement and we compare the prediction of the variable with the measurement of the variable. So blue one is prediction, so analytical things that I'm doing based on the model, and the green one is using the measurements that I have. So this way would be the one following the causality, the physical causality. So I go from inputs to outputs. I have two ways of doing that. One is to do a direct computation, which means going open loop, basically. I take the model and I just do a free run simulation of the model. The other way, that actually is the one we are following, is to use an observer to predict this output. But there are other approaches. Another approach would be to go the other way around, so invert causality. I go from the measurement that I have, I invert my model back, and then I compare, and then I am able to reconstruct what should have been the input to the system, and I compare it, green path, with the input I have. So this is not so a wonderful idea, because most of the time you cannot invert a model like this. And finally, there is another approach, the one that was basically shown in the previous slide, that are the parity relations. So parity relations are a way to check variables that are somewhere in the middle of your model. And you take two different paths, one starting from inputs and going to the middle, and one reconstructing back from the outputs and going to the same variable. To explain how parity relations work, we need to introduce a different interpretations of these variables Z1, Z2, and Z3. So allow me to be a little bit less rigorous, but I hope you can still follow. So let us assume now that Z1 is not a single variable, but Z1 is representing both the state of the system and the input to your system. And then let us assume that Z2 is the derivative of the state and Z3 is the measurement, Y. Okay. So what parity relations are doing is to check this forward relation, which means to compute x dot using the model, which generally we write as some nonlinear function of x and u. And then to do the inverse check using the measurement. But for doing this, you need to take a derivative because you want to get here to x dot. So starting from y, you need to compute the derivative of y. And then the check is, are they the same? Because if we assume that the measurement y is indeed equal to the state, so simplify assumption, then in theory, you should be able to take y, compute the derivative, and this is going to be the derivative of the state, and this should be equal to the dynamical function f that you computed in the direct path. So using this position of variables, we can some way understand what parity relations are doing. There is anyway a big problem. So y is affected by noise. So if you take the derivative, you're amplifying high frequency noise a lot. So checking this, it's really difficult because this is really noisy. So computing this green, the y dot. So there are some workarounds. So you can introduce filtering of the output to reduce the effect of the noise. But then at this point, if you're filtering the output, then you can just implement an observer, because the observer, if you remember the equation, is basically doing that. It is filtering the estimation error on the output in order to reduce the effect of the noise. So we are not covering any longer the parity relation, and we are directly presenting this approach using the observer that has many advantages, and it is more robust. And it can work also for cases where the output equation is not invertible. So if this is not invertible, the parity relation is not working. But this one, you can always check, because the direct path is going all the way up to the measurements. So you can just check something that you compute forward with a measurement that you have. So there is no way that you cannot apply this to a system. So this is going to be our choice. Okay, and now let us anticipate the definition of the other main character here, the threshold. So in the next lecture, we are actually computing it, but today we introduce the definition. So the threshold is the maximum expected value of a function of the residual under healthy conditions. So this, again, is representing physiological limits of the residual. And why do we need that? Well, it is, if you remember in the limit check case, we introduce thresholds because normal physiological behavior is occurring over a wide range. And if you don't have a model, if you have no information, there is no way to tell where in that range you're going to be at a given moment. In the case of the model-based approach, it is slightly different because we have a model, so we can compute what should be the output of the system, but still we cannot compute it exactly. Still, we need to allow for some physiological variation. And why? Because when we are following this path, first of all, we are using equations in our model that are nominal but are not perfect. So by following this path, we are accumulating some error. So this is the difference between the real physical behavior and our model. But finally, when we take the measurement here, we have the measurement noise, the eta that we introduced previously. And yeah, actually, to be complete, let us introduce it here as well. So we need to account for the presence of that. And when we take the difference between the measurement and the prediction, we both have the effect of this noise, let's say uncertainty on the equations, and this measurement noise. So we don't want to issue an alarm just because of the noise, because noise is always there, it's physiological. So we need a way to account for its presence. So we need to introduce an upper limit of what is the maximum value of the residual that we get because of those uncertainties in the model and in the measurements. Anyway, when we exceed these limits, then our null hypothesis, the system is healthy, nominal, is falsified, and then we detect a fault. What's happening, hopefully, then, when you apply this, and if you have a fault at some time, is that your residual, or a function of that, in this case we are taking the absolute value of that, will cross the threshold here. And the time it is happening, it is called the detection time. And you can imagine that a good model-based approach is one where the detection time is very close to the fault time. And also one where you always have a detection, or at least you have it for the cases that matters most. You can easily understand that here we have some change in the residual because of a fault. So the change that you see here is due to a fault. But if the fault is very small, then the effect on the residual is small itself. And maybe the residual will stay here, and the change is not enough to make it cross the threshold. Because you see here, the threshold is pretty much constant because the effect of the uncertainty in the measurements is not going to change over time a lot. And the effect of the uncertainty in the model, well, it depends on your trajectory. But if your system is not moving too much, let's say, and if your model is quite consistent, so the uncertainty of the model is pretty much the same across all possible trajectories, well, then the threshold is not going to change a lot. So we already introduced in previous lectures these dichotomy, this contrast, this conundrum between being sensitive and being robust. So having a high true positive rate and a low false positive rate. And when we go model-based, this translates to having a threshold that is high enough such that we don't have too many false positive, but also having a threshold that is small enough such that we have a lot of true positive, even for small faults. As you can understand, it is not possible for the threshold to be at the same time large and small. So we need to set for some compromise, some in-between value that will give some good true positive and good false positive rates. And we're going to see formally how we can check these and how we can derive a threshold analytically that has good properties. So now that we have the basic concepts in place, we can introduce our formulation more mathematically. But maybe first of all, a question. So we have shown that we can either use direct computation or an observer to do this kind of check following the physical causality of the system. The first question would be, why an observer and why not direct computation? Because some way I'm already telling to you that we are going to use an observer. Well, the thing is that if you do direct computation, you mean that your model is fed the same input as the plant, and it is producing in open loop, so free run simulation, an estimate of the output, and then you check it against the measurement of the output to compute the residual. Instead, in the observer, you are also feeding the actual measurement, and this is used to compute inside the observer basically the residual, that is the difference between the estimation and the measurement, and this is going to correct the dynamics of the observer. So in an observer, you have something like this. Let me write here. So for a linear system, the observer is something like this. You have the nominal equation computed using estimated state, and then you have a feedback term with some gain L, where you have your estimation minus the measurement. And the estimation of the output is computed using the nominal equation like this. So this is the observer equation for a linear system in continuous time, so a Leuenberger observer. And the direct computation would have everything apart this. And the observer instead has also this. So this output error feedback here that is injected in the state equation. And if you remember from control systems courses, the purpose of that is to keep the observer tracking the system. Because if you have this approach, without this term, something like this is happening. If the initial output of the system is this one, so this is y, and this is y at time 0. But you don't know this, so you are starting your model assuming 0 initial condition, because this is what you know at the beginning. You're starting from here. So first of all, you are already off because you don't know the initial conditions. But then the problem is that your dynamic model is not perfect. So in this simple example, the rate at which this is increasing is different than the rate where the real system is increasing. And so you have an error between reality and model that will increase over time. No way. So you have uncertainty in your model is not perfect. If you do a free run simulation, over time you integrate this error and you are drifting away. Instead, in an observer, this is not happening. So even in the same situation where you don't know initial conditions, what the observer is doing is that thanks to this term, it is tracking your output and then staying on that. Of course, this is not exactly the same, otherwise there would be no point. You can just take the measurements. So the difference is in the noise. So the observer is basically low-pass filtering the measurement noise and the uncertainty in the model. So this part here is implementing a filter in the end. But this long-term drift is something that is corrected, because this long-term drift is basically some low-frequency behavior, and is not going to be filtered by this. It is going through that, and so it is used to correct the estimation. And so this is the reason why we need observers, because observers will track your system well under suitable assumptions. So if you design your observer well, then the residual will always be bounded. Instead, in this case, it can grow unbounded. And you can easily see that if you want to define a threshold on something that is unbounded, then you are in troubles. So you cannot apply this approach. No. You need an approach like this one. Okay, let us now introduce the model. So we said we are going to use one. So which kind of model are we using? We have two possibilities when dealing with dynamical systems. The one is to use a continuous time model, and the other is to use a discrete time model. So for theoretical analysis, for results, it is more convenient to use a continuous time model. But when we are going to implement that anyway, we are going to implement it on a digital computer, so the discrete time one is going to be our choice. But both these and these are some nominal model. So we assume that we know everything. We have some function f that is the nominal dynamics. In reality, as we said, it is not like this. So in reality, in discrete time, we have other two contributions to the equation. We have uncertainties here, and we have the fault. Not always, but at some point, we are going to have the fault. So the uncertainty is this function eta of x, u, and k. So we're now going to introduce two different uncertainty symbols. So the first eta is used now for the uncertainty that is called the process uncertainty, the uncertainty in a model. And it's something that for now we just consider unknown, uncertain. And then we have the fault. The fault is expressed here as an additive term. So we have a fault function phi that is a function of x and u. And with respect to what we have seen previously in signal-based approaches, this is one of the key contribution of the model-based approach, because now the fault itself is described as a model. So we have an equation telling us that for a given state and input, the fault is behaving like that, this function phi. So it is not just some exogenous signal doing something, it is a change in the behavior of the system. And this is usually what happens in systems. So you can have some parametric fault that is changing this, some actuator fault that is changing this as well. One thing is that, as we said, the fault function is not always present, and so is not always affecting. So when we are in nominal condition, in healthy conditions, then this should not be in the equation. So the way to account for that is to introduce this function beta. Beta is called the fault profile. It is basically a switch. It is 0 in nominal conditions, different than 0 when the fault is present, and can either be abrupt, incipient, or intermittent. So the behavior we have seen in one of the first lectures. In defining our model, we need also a measurement equation. And to make the presentation simple, we consider the case where we have full state measurements. So the measurement is y equal state x plus another uncertainty, that is, in this case, the measurement noise. So these are the assumptions so far. But actually, in the case where you have a general measurement equation, you can still use the model-based approach using observers. So as we said, beta is a switch. Can either be 0 or 1 before or after the fault instant. So K0 is the fault instant. Or can be incipient, for instance, using this exponential time behavior. But you can also have whatever other function for beta. The only requirements, of course, it is 0 in nominal conditions. And then the fault function itself, phi, can be anything that changes the dynamics of the system. So for instance, we can have an actuator fault. Let us assume that this is making u in faulty condition to be equal to 1 minus theta that multiplies the nominal u. So this theta is a parameter describing the magnitude of the fault, which is between 0, no fault, and 1, so complete loss of the actuator. So how we can implement this kind of fault using the modeling approach that we chose before? Well, it is simple. It is just algebra. So in the healthy case, we have that x dot is equal to f of x and u. In the faulty case, we have that x dot is equal to f of x 1 minus theta u. And you can simply implement these if you define phi, the fault function, to be f of x 1 minus theta u, so the faulty minus the healthy f of x u. So as trivial as it can seem, but basically it is just algebra. So if you introduce this in the previous equation, what you're going to have is that the healthy behavior is cancelled out here, and it is replaced by the faulty one. So you can do it, of course, also for process faults where f is changed in other ways. And we are not covering it explicitly, but also for sensor faults, you can do something like this. You need to introduce a new function phi, so one that is affecting the output equation. So for the output case, you can have simply this. Y in the faulty case is equal to x plus the noise, it is always there, plus some other function phi of y that we call function of x, u, and possibly also the noise. This is to account for the case where the fault is introducing stuck at value behavior. So if your faulty output gets stuck at some value c, can be 0, can be some other value, I don't know, a short circuit in the sensor, so you get just a constant value, then it means that phi of y should be equal to c minus x minus xi. So this is why this fault function on the sensor should also include this, for instance. In order to proceed forward and to be able to present some of the theoretical results on the robustness and the detectability performances of the approach, that is, how is a false alarm rate, how is a true positive rate, we need some formal assumption. The first one is that when we start, we have no faults. So at time k0, there are no faults in the system. Also, we need to assume that even when we have a fault, the variables, the state and input, and of course also the output, they stay bounded. So the fault is not immediately causing a catastrophe. So I know that this is a sort of strange assumption because you say, okay, we want to prevent catastrophes. So if we just assume they are not going to happen, then we solve the problem. But indeed, this is just a mathematical thing. We need that to hold for the time during which we are able to detect a fault. And when we detect a fault, then we can accommodate it. If you remember all the chain of events leading to fault tolerance. And if you are fast enough, there is no catastrophe happening. So this assumption is still reasonable. And then we need some assumption of the fact that the time profile parameter B, the time profile parameter is the one occurring here, is unknown, but it is bounded. So it cannot be anything. And this kind of assumption, you see, they are going to occur a lot in the model-based approach, because in order to compute a threshold, in order to bound the residual, you need all the sources of uncertainty, the things that will make the residual big, of course, to be bounded. So if you have infinite uncertainty, okay, then your residual is going to be unbounded, and you cannot have a threshold. So this is the reason why we need these assumptions. And so indeed, the next assumptions are on the uncertainty. So we need them to be bounded. And we don't know how they are behaving, just we know that they are bounded. And we know the value of the bound. So this is assumption 3. In particular, we are making this assumption for each component of the uncertainty eta. So eta is in general a vector, because in the state equation, x dot equal to f of x u plus eta plus so on. Well, x usually is a vector, so eta is a vector as well. And for each component I, we assume that the absolute value is bounded by some function that we know. And this will be the key thing for building a threshold analytically. Similarly, we assume that the uncertainty in the measurement is also bounded, and we know the value of the bound. So if we really don't know things, at least we can have some conservative bound, because in physical world, not everything is possible. So an uncertainty that is unbounded is not physically reasonable. So if we have some knowledge about the process, some knowledge about the model that we identified, some way of the system, we can also come up with a bound on the uncertainty. So indeed, one big issue that I didn't tell you so far is that having a model of a system is quite a big assumption. So model-based approaches are powerful, as I anticipated and as I will show, but they are costly because assuming to have a model is quite an assumption. Getting a good model of a system is not easy. So it takes a lot of resources to identify it, and even more resources to characterize these bounds. But if we are able to do that, then we can get some very good performances. Okay, now how we introduce the observer. So I scribbled before how to write the equation of a Leuenberger observer in continuous time. Now let us write how to get the equation in discrete time, because this is where also we are working most of the time. So in discrete time, we introduce the estimate x hat of the state, and the dynamical equation of x hat is this one. We apply the nominal dynamics on the measurement. And we can do that because we have this assumption, you remember, that y is equal to x plus xi. So we would need to apply that to x, but as we know y, we can apply it to y. We are just introducing some uncertainty because the measurement is noisy. U we know because it's computed by the control system. And then we have the output error feedback term, the one that is dampening out uncertainty and making the observer track our system. So you remember in continuous time we had a minus here, but in discrete time we have here a plus. And lambda is a gain matrix, and the important thing is that lambda is such that this equation is stable. And in practice, in discrete time, what you want is that the absolute value of the eigenvalues of lambda, they are inside the unit circle. So they are less or equal to 1. So this is the condition for the stability of this one. It is really simple because basically we have this term here, the dynamics of the system is something that is directly computed from measurements. So it's from the observer point of view, this is coming in as an external signal. Would have been different the case where we don't have full state measurement and we need to use, instead of y here, we need to use x hat. So if here we had f of x hat and u, then the stability would have been less trivial. For the case I presented before, in continuous time anyway, if you work out the dynamics of the estimation error of this observer, at some point you get a matrix A minus LC. I guess you can guess how you get this because you have minus L here. Y hat is equal to Cx hat. So you guess how you get this. And this is the matrix whose eigenvalues need to be stable in continuous time when you are using the estimate x hat here in the general case. But in our simplified case, we have the measurement of the state. So we can directly plug that in here, and so we simplify that a lot. It may seem trivial, but still this observer is dampening out measurement noise. Still, it is doing some useful thing. So at this point, the residual is y minus y hat, which basically means that what you have here is equal to minus the residual. Okay, so this is the observer. What we are interested in now that we introduce the equations is to compute a solution for the dynamics of the observer. And the interest is motivated by the fact that if we have a solution for the residual, and if we can bound that solution, we can use that for a threshold, because this is what the threshold needs to do, to be an upper bound on the possible behaviors of the residual. So in order to do that, let us expand what we had before. We start by writing the value of r at time k plus 1. And you will see in a while why I am interested in time k plus 1. So this is equal to our noisy measurement y at time k plus 1 minus the estimate y hat at time k plus 1. And now what we can do is to expand this. Now we need to remember that the measurement equation is simply y is equal to the state plus the uncertainty on the measurement psi. So we can expand this output equation here. So what we have is the next line. So this is equal to the state at time k plus 1, the true one, plus the uncertainty at time k plus 1 minus the estimate of x at time k plus 1. Okay, so far we expanded the output equation. But now we can expand further, and we can use the state dynamics, and we can use the state dynamics and expand it here. So now we have f of x of k and u at k plus the uncertainty eta. Let me write just eta of k for short, plus the measurement uncertainty at time k plus 1. And I don't have the fault here, because now we are assuming to write the residual dynamics under the null hypothesis, so in nominal conditions. And now I need to expand this. So this one is equal to minus f of what? This is f computed using y, the measurement at time k, which unfortunately is uncertain. The input u at time k that we know. And then we also have, minus again, we also have the output error injection term. So that was lambda that multiplies the estimate of the state y hat time k minus the measurement, which is uncertain at time k. Now that we got here, we can actually rearrange and group terms, and we can then write lambda that multiplies the residual r of k. Because if you remember, this y hat minus y is minus the residual. So minus with minus, it goes away. So we have lambda that multiplies r. And then we have all these terms. So let us rewrite them in a nice way. We take this and we write it as f of what? X is equal to y minus psi. So let us write it like that. Y of k minus psi of k, and then u of k, minus this stays the same. So f of y of k, u of k. And then what is left is these two uncertainty. So plus eta at time k plus psi at time k. And finally, we can write it as lambda that multiplies r plus a new term that we define now, delta of time k, where this delta is all these terms together. So why we did that? Because we want to show that the dynamics of the residual are like this. Would have been nicer to use blue from the beginning for r. So r at time k plus 1 is equal to lambda at time, lambda that multiplies r of time k plus this delta. So this is the equation of a simple first order system whose eigenvalues depends on lambda. But we know that lambda is a stable discrete time matrix. We said plus this that behaves like an external input. And what is this actually? So this delta is a term accounting for all the uncertainties that we have here. So we have a lot of them. So we have this first part is f computed using the true state minus f computed with what we know. So this is a sort of difference between the dynamics, the nominal dynamics that is actually occurring and the one that we think it is occurring, because we only have access to y, which is a noisy measurement of x, plus the effect of this process uncertainty plus the effect of the measurement. And sorry, there is a small mistake here. It is not k, but k plus 1. Now, if delta is bounded, then the solution to r is bounded as well, because this is a stable linear system. So bounded input, bounded output. So can we assume this is bounded? Well, yes, we can, because thanks to the assumptions that we had in place before, we know that this is bounded. We know that y is bounded. F is a bounded function. I don't know if I mentioned that. F also should be assumed to be bounded. Then all the things that you have here, they are bounded. So under the assumptions that we have, we can prove that our residual solution is bounded. And that's great, because then we can compute that bound, that upper bound, and then we have a threshold. So this is the whole purpose of what we are doing. So nothing here is really complex. It is just algebra, but I just wanted to show you how you get here and how the different components of the uncertainty that we have are concurring to this final total uncertainty term delta. So uncertainty in the model, in the measurement, and uncertainty in applying the nominal model with uncertain measurements. That was the introduction for the first part, so for this first lecture. So we introduced the model-based fault detection via observers, and we introduced the residual dynamics. So in the next part, we are starting from this and computing a bound on that in order to introduce the thresholds. And once that we have the thresholds, we can analyze detectability and robustness properties of this approach. And finally, we will provide an example.